In Chapter 3 we will now perform the consequence analysis. So first we need to define the first model for a toxic rupture. In the tutorial study folder, move to the Models tab. The first model you will define represents the rupture of a vessel containing a toxic material, which is one of several models dealing with a toxic material. Insert a folder and name this folder Toxic. You will place all the models that represent toxic releases in this folder. Turn on the option to insert models on the map. So in the options menu, turn this option on. If you turn this option on, then the model icon will not appear in the study tree until you have clicked on the map to set the location for the model. In this tutorial, you will insert the models on the map in approximately the correct location, and then the correct location is necessary for the input dialog. So firstly, we'll insert a vessel pipe source model. So select the toxic folder, then select vessel pipe source model from the insert menu. The map window will open if it is not already open, and the cursor will turn to a crosshair. And you should click at a point near the centre of the site to place the model. After you've clicked, an icon will appear in the study tree and a dot will appear on the map to show the location of the model. Rename the icon CL2 Rupture. The icon will have a red border around it, showing that it does not have a full set of input data. You will not be able to run consequence calculations for the model until you have supplied values for all the mandatory fields. Use the vessel pipe source model when you want to perform a dispersion and effects calculation for a release from a contaminant, and you want to use the program's inbuilt discharge calculations to determine the state of the material after expansion to atmospheric pressure, which is the state required for the start of the dispersion calculations. The program contains a second source model, which is called a user-defined source model. This model does not perform discharge calculations, but instead allows you to specify directly the state of the material after expansion to atmospheric pressure. To set up the input data, double click on the icon for the model to open the input dialog. All of the fields in the first tab section are blank, and those that are enabled have red borders. A field with a red border is a mandatory field which you must supply a value for, and you will not be able to run calculations for a model until that mandatory field has been set. This section describes each tab section in turn, including those that are not relevant to this particular hazardous event. Click on the Help button to open the online help if you want further information. The Materials tab section. So in this section, we will set the discharge material by clicking on the button with the three dots to the right of the discharge material field and selecting chlorine from the list that appears. The list contains all of the materials that are defined in the system materials. The vessel is a sphere with a volume of 120 meters cubed. This model will represent the vessel with the maximum degree of filling, which is 85%. So select volume as the method of specifying the inventory and enter a value of 102. 85% of the 120. The chlorine is held under saturation conditions at atmospheric pressure. The temperature will vary depending on the season and time of day, but for this model, a value of 10 degrees Celsius can be used as a representative. So the process conditions are temperature of a saturated liquid set to 10 degrees C. Once you've set the temperature field, the pressure field will become automatically set from what you've entered. To define the process conditions for a material that is not held under saturation conditions, such as a gas or a padded liquid, you must select both temperature and pressure from the list and give values for both. The Risk tab section contains data that are used in the risk calculations, but not in the consequence calculations. If the calculation mode is set to consequence only, this tab will not appear in the dialog, and you will only be able to run consequence calculations. So set the event frequency to 0.00001 per year, so that's 1e to the minus 5. The other fields in this tab section are all disabled for this model because they are not applicable to a material that has only toxic properties and no flammable properties. So moving on to the scenario tab, you use this tab section to specify the type of hazardous event that you want to model. The range of types available will depend on the process conditions you have specified. There is only one scenario type available for modelling the rupture of a pressurised vessel, and this is the catastrophic rupture, which is selected by default. The other scenarios are either longer duration releases or applicable only to insulated tanks. The vessel is outdoors, so you can leave the outdoor/in-building fields with the default section of outdoors. If you select in-build release, the program will model the build-up concentration inside the building, and the dispersion calculation will start with the state of the plume as it is released from the ventilation system. The other fields in the tab section are not relevant to a rupture scenario. You can take the default settings for all of the fields in this tab section. In the pipe tab section, all of the fields are disabled when the scenario is set to rupture. They are relevant only for a line rupture, disc rupture, relief valve and long pipeline scenario. In the vessel tab section, all of the fields are disabled when the scenario is set to rupture. For all of those other scenarios, some of the fields in the tab section will be enabled, with a combination depending on the scenario that you've picked. In the location tab section, there are no mandatory fields in this tab section. The elevation has a default value of 1 meter taken from system parameters, but you should set this to 7.37. This is the elevation at the centre of the sphere above the ground. If there are particular locations that you're interested in, you can enter values for the distances. These results for these distances appear in the summary report. For this tutorial you only need to set the elevation. The bund data tab is used if there is a bund around the vessel and you want to take this into account in the modelling of pool spreading and evaporation. You can check the bund exists box and enter a description of the bund. For this sphere there is no bund, so you can leave the tab section with the default values. The indoor-outdoor tab has all its fields disabled when the scenario is a catastrophic rupture outdoors. Some of the fields are enabled for a continuous scenario, as you will see later, while others are enabled for in-building releases. The flammable tab section has fields that are disabled when the material is toxic only. For a flammable release, they allow you to set variables for jet fire and explosion modelling. The toxic parameters tab field is used in modelling the build-up of toxic concentrations inside buildings located downwind from the release and the exposure of people inside the buildings. For this tutorial you can leave all fields with their default values. The TNT, multi-energy and Baker-Strelo fields are disabled when the material is toxic only and are not used in the explosion modelling for a source model. And the discharge parameter tab section is always enabled and take the default values from the system parameters. They are used in the discharge modelling for the line rupture, disc rupture and relief valve scenario and are not relevant to this model. When you've finished editing the input data, OK the dialog and run the model for the CO2 rupture 9. When the calculations are complete, view the graph for all the weathers. You will see that there is no pool vaporization tab in the graph window, which means that the liquid in the release did not rain out. To see the effect distances that will be used in the risk calculations, move to the toxic tab and then view the lethality graph. The greatest effect distances are for the f1.5 meter per second weather, with a distance of about 2.5 kilometers to an outdoor lethality level of 10%. The shortest downwind effect distances are for d5 meters per second indoor, which reaches approximately 60% of the distance of f1.5 meters per second for a lethality level of 10%. We will now define a second source, a toxic liquid from Pipework. The second release is from the same chlorine sphere, but the hazardous event is a rupture of a 1-inch liquid line attached to the bottom of the sphere, where the initial liquid head will be 4.6 meters. The line runs 4 meters vertically downwards to 10 centimeters from the ground, then 5 meters horizontally to an isolation valve. The rupture is assumed to occur just before the isolation valve. So make a copy of the first model, and paste it into the toxic folder, and rename the copy CL2 liquid pipework. Open the input dialog for the CL2 liquid pipework and leave the material and risks tab sections as they are. The material and process conditions are the same as for the rupture, and for this tutorial the location and event frequency will be taken as being the same. For pipework failures, the frequency represents a specific length of pipework, e.g. the length between the sphere and an isolation valve. In reality, the release location would be offset by a few meters from the centre of the sphere. However, this difference is insignificant compared with the effect distances for the chlorine and can be ignored. In the Scenarios tab section, set the scenario type to line rupture and the phase to be released to liquid. The line rupture scenario models the full bore rupture of pipework attached to a vessel, and the discharge calculations take into account the effect of friction in the flow from the vessel to the point of rupture. To model a release from the body of the vessel with no frictional losses in the discharge, you would choose the leak scenario. On the pipe tab section, the pipe length is the length of pipework between the vessel and the point of rupture, and you should set this to 9 meters. To set the internal diameter to 1 inch, click on the millimeter to the right of the field, change it to inches, and enter 1 inch. You can then enter the diameter directly in inches rather than having to perform the conversion yourself into the default units of millimeters. Leave the pipe roughness with the default values from the system parameters. The number of valves is used in the modelling of frictional losses, and you can leave them as 0. The other fields in the tab section are not relevant. For the line rupture scenario and most other scenarios that involve continuous release, the time varying release option can be enabled in the vessel. If you do not check this option, then release will be modelled with the initial release rates, and the duration will be the time required to drain the inventory at this initial rate. This will normally give conservative results in the consequence and risk calculations. If you select the time varying option, then you must supply information about the dimensions of the vessel. The discharge calculation will model the effect of the release on conditions in the vessel and the way that these conditions and the release rates change over time, and will represent these time varying results either with a single rate or with a series of rates, depending on your selection for the rate versus time. For this release, you will perform an initial run of the discharge calculations with the time varying modelling selected. So set the time varying release option, set the tank type to spherical, the height of discharge to 0, and the diameter to 6.74 meters. Leave the rate versus time set to the default selection of averaging rate with a duration of interest of 3,600 seconds. On the location tab, set the elevation to 0.1 meters. With this setting, the liquid droplets will probably not evaporate inside the clouds and will probably rain out and form a vaporization pool. In the geometry tab section, leave this unchanged as the line rupture case represents the same vessel location. There's no bund specified, so the bund data tab can be left with the default values. On the indoor-outdoor tab section, for a continuous release scenario such as a line rupture, you must specify the direction of release. Choose horizontal from the list, which is the correct setting for this type of unobstructed rupture of horizontal pipework. The list of directions includes the second horizontal option, horizontal impingement. You can use this option if the release is in a congested area and the release is likely to impinge on a wall or other equipment. program will reduce the momentum of the release, which will reduce the amount of air mixed into the jet during the initial stages. On the Discharge Parameters tab, there is one bend in the 9 meters of pipework, so you can set the frequency of bend to 0.11 meters. And OK the dialog. We are now going to run the discharge calculations. Select the model and then select Run Discharge from the Run menu. This will run the discharge calculations alone without performing the dispersion and effects calculations. When the results are complete, view the report and move to the TV discharge report. The rate drops by less than 3% in 2 hours of release, so the time varying behaviour can be ignored for this release. There are two options for bypassing the time varying discharge modelling in this situation. The first is to use the average discharge results to create a user-defined source model. When you perform the discharge calculations, the program calculated the average rate over the first 3,600 seconds, and this is the representative rate given in the discharge report. If you decide that you want to use this average rate rather than the initial rate, you should select the model and then select Create Source from the Edit menu. The program will show a list of the weather conditions for which you perform the discharge calculations and for which it has results. And when you select one of these weathers, the program will create a user-defined source model with the name Calculated Discharge. The user-defined source model has many of the same tab sections as the vessel pipe model, but instead of a scenario, vessel and pipe tab sections, it has a discharge tab section, in which you specify the discharge rate and conditions directly, since the user-defined source model does not perform any discharge modelling itself. The calculated discharge model will be created with discharge data taken from the average results from the liquid pipework model, but you can edit these values if you choose. The second and simplest method for bypassing the time-varying discharge modelling is to edit the model and deselect time-varying release. So if you go to the Vessel tab and deselect the time-varying release option, the discharge calculation for this model will run much more quickly. Set the tank head to 4.6 meters and OK the dialog. We are now ready to run the consequence calculations and view the results. Set the current run row to the night run row, since this is the most stable weather conditions and will give the longest dispersion distances. Then select the model and select Run Model from either the Run menu or the toolbar. When the calculations are complete, view the graphs for all the weathers. You will see that there is a pool vaporization tab in the graph window, which means that the liquid in the release did rain out. To see the effect distances that will be used in the risk calculation, move to the Toxic tab and then view the lethality graph. The greatest effect distances are for the f1.5 meter per second weather outdoors with a distance of 900 meters to a lethality level of 10%, which is approximately a third of the distance reached by the catastrophic rupture. The least stable nighttime condition, the 5 meters per second, reaches only 350 meters for 10% lethality outdoors. We are now ready to define the third model, toxic vapour from pipework. The vapour release is a rupture of a 2-inch pipe attached to the top of a sphere. The line runs 3.4 meters horizontally then vertically downwards, and the rupture is assumed to occur 1 metre from the ground. Create a model as a copy of the liquid pipework model. And rename the model CL2 Vapour Pipework. Change the input data. On the Scenarios tab, change the phase release to Vapour. On the Pipe tab, change the pipe length to 13 metres and the internal diameter to 2 inches. On the Location tab, change the elevation to 1 metre. On the Indoor-Outdoor tab, change the direction to down, impinging on the ground. On the Discharge Parameters tab, change the frequency of bend to 0.08 and OK the dialog. We will now define 3 flammable releases. There is a propane sphere at the far north of the site. The propane sphere has the same dimensions as the chlorine sphere and the same design of pipework, and is also operating under saturated conditions at atmospheric temperature. When setting the input data, you can define the rupture and the 2 pipework failures by copying the 3 toxic models and simply changing the selection of discharge material and the eastern coordinate as shown. Select the toxic folder, copy and paste it, and name the copy Flammable. In each of the names of the models, change it from CL2 to C3. Open the input dialog for each of the models in turn, and in the Materials tab, change the discharge material from chlorine to propane. When you return to the Materials tab section, you will see that the program has recalculated the saturation pressure at 10 degrees C and also the mass of the inventory. You now need to change the location. So in the Geometry tab section, set the eastern coordinate to 197.635.95 and the northern coordinate to 435.611.19. Once you have updated all of the models, you can run the consequence calculations for all 3 flammable models at once. Set the run mode to night, and then select the flammable folder and use the run model option. You can also view the results for all 3 models at once. Select the flammable folder and then select View Graphs. A plot setup dialog will appear, prompting you for the weather for which you want to view the results. When you are viewing results for multiple models, you can only choose a single weather. So the weathers have radio buttons beside them, whereas they have checkboxes beside them when you are viewing results for a single model. Select the f1.5 meter per second weather and OK the dialog. The graph window contains tab sections of concentration graphs as with toxic model, but it also has Jetfire, Fireball and Flashfire tab sections instead of the toxic tab section. The propane release did not produce any liquid rain out, so there are no pool fire tab sections. The main features of the graphs are now described. The Jetfire graphs. The Jetfire tab section contains 3 graphs, which are presenting results for the 2 pipework failures. One graph shows jet fire radiation intensity versus distance. The second shows intensity radii to a radiative level set in the system parameters, and the third graph shows lethality radii to a lethality level of 1%. The maximum downwind effect distance shown in these graphs is about 28 meters, which is the distance for 1% lethality for the liquid release. In the fireable graphs, the fireable tab section also contains 3 graphs which are presenting results only for the rupture. The maximum downwind effect distance is 290 meters to a lethality level of 1%. The fireball lethality radii graph show the results for a range of lethality levels between 100% and 1%, which is different from the jet fire lethality radii graphs, which only show results for a single lethality level for the 2 pipework releases. This difference illustrates an important aspect of the way that graphs work in the program. If a given graph is displaying results for more than one weather or model, then it will be giving results for a single effect level, whereas if the graph is displaying results for a single weather or model, then it will be able to give results for more than one effect level, if more than one level has been calculated. This means that if you want to view graphs that show the full set of effect levels for a given model, you must view the graphs for a single weather at a single time. The flash fire graph shows the zones for the cloud at the time that it covers the maximum area. For the rupture, this gives a maximum downwind effect distance of about 350 meters to 10,000 ppm, whereas for the 2 pipework releases, this gives a distance of 75 meters to the same concentration. 10,000 ppm is 50% of the LFL, which is the fraction set by default in the flammable parameters at the boundary of the flash fire effect zone. Note that the effect zone consists of the dispersion envelope rotated through all wind directions. We will now set up a flammable release from a rail tank wagon. We first need to define the rupture of the wagon, so create a folder and name it tank wagon. And then copy the rupture model from the flammable folder which we'll use as a starting point for defining the release. Name the model Wagon Rupture. Now open the input dialog. In the Materials tab, change the inventory to 43.2 meters cubed. In the Geometry tab, change the northern coordinate to 435,581. In the Locations tab, change the elevation to 1.8 and OK the dialog. Now copy this rupture model and name the copy Wagon Liquid Leak. And open the input dialog. In the Scenarios tab, change the scenario type to leak and the hole diameter to 1 inch. In the Vessel tab, change the tank head to 1.95 meters and in the Location tab, change the elevation to 0.5 meters. And in the Indoor-Outdoor tab, change the direction to down, impinging on the ground, and OK the dialog. We now need to define the fireball failure under flame impingement. The program allows you to model immediate ignition effects from fireballs and pool fires on their own, separately from the other models of dispersion and delayed ignition effects, and you do this by using the fireball model or pool fire model rather than the source model. Select the tank wagon folder, and then select the option to insert a fireball. Click on the map on the dot to the north of the site that represents the tank wagon. Then open the input dialog and set the data. Set the material to propane. And the burst pressure to 8.57. On the risk tab, set the event frequency to 10e to the minus 5. On the geometry tab, set the eastern location to 197327 and the northern location to 435581. And then on the fireball shape tab, set the release mass to 22.2 e to the 3 and the mass vapor fraction to 0.25 and OK the dialog. You're now ready to run the calculations and view the results. Set the current run mode to day, since transport takes place only during daytime, and run the calculations for all three models. When the calculations are complete, view the graphs for all three models and select the D 5 meter per second weather. Then examine the fireball results. The fireball model gives slightly larger effect distances than the Wagon Rupture model, with a distance of about 205 meters for 1% lethality compared with 190 meters. This shows the effect of the higher vessel pressure used in the fireball model to model failure under flame impingement, whereas the Wagon Rupture model considered a rupture under normal operating conditions, which then has a probability of igniting immediately and giving fireball effects. You've now completed your work on the Models tab section of the study tree, which completes this chapter of the tutorial. You should save the study folder at this point and proceed to the next chapter whenever you're ready.